fourth type of solution calculation that we need to talk about is called molarity. Molarity is not something that you'll see a lot of in your nursing practice, whereas those percent solutions were. But molarity is used by far the most often in chemistry. And so it bears some sort of attention here because, well, it's the easiest of the solution calculations to use when it comes time to figuring out other things, especially in the lab. Okay, so molarity is abbreviated capital M, and it stands for, or it's calculated by taking the moles of your solute divided by the liters of solution. Now this is an important thing to talk about. We're talking about liters of solution. That's a very specific, defined unit. It doesn't mean just volume of our solution. It means that we have to calculate volume in liters, otherwise we don't get the right answer. Okay. So that's molarity. Now, sometimes you'll need to calculate moles. You already know how to do that. All you have to do is use your molecular weight and use that as a unit conversion. If you have 5.61 grams of sodium hydroxide, let's say you have a 1 liter solution of 5.61 grams of sodium hydroxide, and we need to find the molarity. Well, molarity is not grams solute divided by liters of solution, it's moles. So we need to take those grams and put that into moles. And here is where you're going to use your molecular weight. 1 mole of NaOH divided by the number of grams. I don't know that off the top of my head. 22 plus 16 plus 1. I think it's like 38 something. I don't know. You have to calculate that. And that'll give you your answer in number of moles, which is what you can then put into your formula. So sometimes you have to do an extra step here in order to, excuse me, to plug and chug. Okay, let's do some examples of this molarity business. Calculate the molarity of a solution that contains 2.50 moles of KNO3 dissolved in 5 liters of solution. Start with your table of knowns and unknowns. Okay, I'm going to work from left to right through my problem. Calculate the molarity. That means M equals question mark. 2.5 moles. Mole solute equals 2.50 moles. And dissolved in 5 liters, liter solution equals 5.00 liters. Break the formula down. Now you see what I did there? I abbreviated things already. We chemists are lazy. We like to abbreviate stuff. So from now on, I'm not going to be writing mole solute divided by liters of solution. That's implied when I write this. And the fewer words you can use in your writing of your mathematical equation, the easier it is to use your algebra. Okay, do we need to use algebra here? Are we solved for our question mark? Yes, we just plug and chug. Mole is 2.50. Liters is 5.00. 2.5 divided by 5. 0.5, right? That's your answer. Now, what does this sound like when we have this written down? We don't say it 0.500 m KNO3. We call it sounds like 0.500 molar KNO3. So when we read the M as a unit of concentration, we call it molar. 0.5 molar KNO3. Let's do number 6. How many moles of sodium chloride are present in 100 milliliters of 0.125 molar solution? Okay. How many moles are present in 100 milliliters of 0.125 molar? Okay, let's work through the text. How many moles? That means moles equals question mark. And then here we have a volume, but we want to find liters. Liters does not equal milliliters, so we have to put that unit into liters. So you're going to divide by 1,000, that gives you 0.100 liters. Now, if you can divide by 1,000 in your head, that's great. Then you don't have to show this step at all. You can just write L equals 0.100 liters. If you have to do the unit conversions with that, that's okay too. And then we have the 0.125, and that's molar. So we have our table all finished. Now, step 2, write down your equation. Step 3, solve for your question mark. Okay, this time our question mark is not big M, it's mole. So now we need to get that L on the other side. How do you undo division? You multiply. So we're going to multiply L by both sides of the equation. That'll give us moles equals L times N. Oh, Michelle, that's weird. Before you had, just in the top, you had mole on the right side. Now it's on the left side? What's that about? Well, I always like my question mark to be on the left side. So I will just interchange, I'll just flip the two sides of the reaction around, or the equation around. There's nothing wrong with that as long as you're not messing with any of the math. You're just flipping the sides around. That's totally legitimate. Now when you've got that unit, all you have to do is plug and chug. Make sure you're using liters and not milliliters. 0.1 times 0.125 equals 0.0125 moles of NaCl. Do I have the right unit? Do I have the right number of sig figs? Yes, on both accounts. Okay, here's what I want you to do on your own. So pause tape and then come back. you've rejoined me, you've probably gotten stuck. Well, Michelle, question mark is not anywhere in this formula. I can't solve for grams. No, you can't. This is one of those ones where you're going to have to convert between moles and grams. What's the information you don't know in this formula right now? So we have to solve for moles. At this moment, you're probably thinking, do I have to write those units every time? You absolutely have to write them every time, and if you don't have units in when you're plugging and chugging, you'll lose points. This is all about form and precision. You cannot be precise if you're lazy and sloppy. Okay, what number is this? 7. So here we know a number of moles. That's not what we're looking for. So here we're just going to use our molecular weight. And just to save space, I'm just going to write 180 grams divided by 1 moles. And that equals always describe what that is, grams or percent volume or molar of. Do I have the right unit? Yeah. Do I have the right number of sig figs? Nope. Should be only one weight. Okay. You should be able to do this on your own now. Don't get this answer, go back and watch me work through all of the problem. Look at your paper. Systematically go through every number, every working that you did, and try to find out what you did that's different than what I did. Okay. I think that's the, yep. Okay. So now we just have one more type of solution calculation to master, and that's what we call osmolarity. Osmolarity is a very special type of solution concentration, and we only measure it in one specific instance. We'll be talking about that in the next part of the lecture, but because it's a solution calculation, I wanted to just go through that right away. Osmolarity is equal to the molarity of your solution times the number of particles. Okay, molarity is easy, we just learned how to do that. Number of particles, what's that about? Well, when I say number of particles, what I'm referring to is the number of species that form in solution. Okay, in order to know what I'm talking about when I'm referring to these particles, we need to talk about electrolytes and non-electrolytes. Electrolytes and non-electrolytes have one thing in common. Both dissolve in water. So that's the only thing they have in common. Non-electrolytes, we'll talk about them first. Do not, this is a chemistry word, dissociate in solution. Dissociate. Dissociate in English means break apart. The only non-electrolyte I want you to be aware of is glucose. Glucose is a non-electrolyte. Yes, sugar does dissolve in water, but no, it doesn't break apart at all. It stays as its C6H12O6 molecule. Therefore, when glucose is in water, it has one particle. This is something to make note of, because that's all I really want you to know about non-electrolytes. Okay, electrolytes are different. Electrolytes can be either strong or weak. Strong electrolytes dissociate or break apart completely. The strong electrolytes are ionic compounds. Sodium chloride, potassium chloride. Sodium and potassium are two very important electrolytes that need to be in your body. You need to consume a certain amount of sodium and potassium within the right ratios in order for your body to function properly. That's biochemistry. We're not going to get into that today. Weak electrolytes dissociate a little. And we're not really going to worry about them. It's the strong electrolytes that we want to worry about. How do you determine how many particles you have in a strong electrolyte? we have 3 strong electrolytes. In order to figure out how many particles you have, you need to actually calculate how many ions you have. Okay, so if you take a look at each compound, here you have a sodium and a chlorine ion. Therefore, you have how many particles? 2. HCl, H plus, Cl minus, 2. H2SO4. Well, you got 2 H's. So you have H plus, and then you have this. Remember, we're not talking about how many atoms you have, or how many ions you have, or how many different, little parts of each thing you have. We're talking about ions. So anything that's a polyatomic ion does not dissociate. So how many particles does H2SO4 have? 1, 2, 3. That sounds so bad. Let's do some examples. How many ions do you have in each of these compounds? I want you to pause it and think about it, then come back. Here you have H plus, PO4 3 minus. PO4 3 minus stays intact. We do not break it apart further. Calcium 2 plus, OH minus, OH minus. 3 particles. And so on down the line. Let's do an example of this from your homework. I can't think of anything off the top of my head. We'll just do a quick example. Calculate the osmolarity of a 3.2 molar solution of Na2SO4. Okay, you can make a table of knowns and unknowns for this. OSM is your question, OSM is your question mark. You're given a molarity, and you know number of particles. How many should you have? This is the easiest and the best formula. OSM equals M times number of particles. Therefore, we have 3.2 M times 3, so that would be 9.6 OSM, and it sounds like osmoles. So 9.6 osmoles of Na2SO4. This number is exact. We do not calculate significant figures from an exact integer. Therefore, we should have 2 sig figs in the problem. Do not overthink these problems. A lot of students get confused and tripped up because they try to overthink it. It really is this easy.